So hi guys, I'm George, or dyreshark. I'm going to be giving a talk on runtimes as they pertain to, well, specifically the JVM and CLR, but whatevs. Credentials, I'm going to throw stuff at you and hope that me passing interviews at certain companies makes you believe in me as a person. I've worked at Data Tactics, Microsoft. This summer I'm doing Google Research. Microsoft was CLR for a bit. Google Research is going to be compiler/runtimes. More bragging, I've worked with C++ for about, well, C with classes and templates for 6 to 7 years, actual C++ for 2 to 3 years, then Java, Python, and general functional programming for about 2 years. So, the content of this talk is really up to you guys. I have lots of spaces where I say, if you're interested, ask me. If you're not interested, we can just continue on and ignore the rambling for 10 minutes. JVM is going to be the main thing that I'm focusing on because that's what I have the most experience with. CLR, I can also talk about C, Python, and LLVM, not so much. I can also go into MRI, which is Ruby's runtime, or at least the default one, etc. So there are so many runtimes, I'm aware. Lots of these concepts will translate from one to the other, to the other, to the other, to the other. These are kind of the foundations of runtimes. Also, when I say the JVM or the CLR, I'm talking about Hotspot, which is the normal Oracle implementation, or Microsoft CLR. All the different JVMs are implemented just a little bit differently, so that it'll make me wrong in every case, but whatever. As a quick aside, questions or I'm wrong, feel free to interrupt. Feel free to say, hey George, please explain this. Hey George, please, do whatever. I present very quick because this is going to be videotaped, and there's a lot to go over. And I don't claim ownership of any of the images in this presentation because I used a lot, and they're all kind of just from the first page of Google Images. So what's a runtime? Audience. Anyone. You can be wrong. I won't hate you.
Specifically in this case, the JVM and the CLR.
Cool. What's a runtime? Audience.
A program that runs programs?
So, as Wikipedia defines it, it can be anything that you really link to that runs a runtime. Like malloc is technically a runtime, and pthreads APIs are technically runtimes. I really don't care. I'm going with runtimes, like you said, JVM and CLR. Yes, I like puns quite a bit, so you might see a few of those. We're going to deal with more complex ones, like I said, and then there's a yay there because I can't stay serious for more than 5 minutes. So generally this will focus on runtimes. Languages higher level than Java. So I have a cup of coffee, and for the fellow Doge fans, I have WoW. So what's in a runtime that we're going to be talking about? Essentially, your program gets compiled at some point to just bytes, i.e. Java bytecode, common intermediate language, or the type C files that you see. And then if you want to add, they're generally stack-based. So you push 2 things onto the stack. You say, pop the 2, add, and then push the result back onto the stack. It's really kind of boring. There are significantly faster ways to do this. If you want a good example, you can look at the Erlang VM. It has an array of go-tos essentially that it indexes into. So that's not actually allowed in most implementations of C, but whatever. They also have garbage collection, so you can do this and your program will never crash. It will just use 100% of the CPU, so it'll feel like Java. They have reflections, so you can say, hey, at runtime, does this have this attribute given by the string? And we have safe get editor and Python there. They have type safety, so you can't cache your strings to integer pointers. You'll get 100 lines of garbage and 1 line of useful. There's more. It's got arrays bounds checking, and I thought that this was kind of cool. Also, it was like the first image when I typed in bounds checking on Google, so I'm not quite sure why. But also, on LLVM at least, this program works like it will compile and run normally. So, stop, we get it. We've got all of these things as well. I don't care. And so, everybody's seen this? I know some of these words like just-in-time, virtual dispatch, memory protection, blah, blah, blah. I'm very serious in case you can't tell.
What is virtual dispatch?
You'll see. I'm going to get a lot into that very soon. So lots of these are very, very long topics. I've gone over, like I've talked to people about garbage collection for hours before. I'm not going to give you that full, in-depth garbage collection talk. It's just going to be a general, like 15-minute, 1,000 foot as opposed to 10,000 foot overview. Also, I'm needy, so we're going to go over these things mainly. Type safety, garbage collection, and JIT. Not in that order. I swapped JIT and garbage collection the last second because, you know, I can't have things the same all the time. Like I said, it's very in-depth topics. Not going to go over them. You need to pay attention to the first one. That's where I explained it. Virtual dispatch. Otherwise, you're not going to get the second two. You can ignore me for the second two. And then this space is initially left blank. So let's go to type safety. So I have this Java code. It's incredibly complex that I had to type it out on PowerPoint. Does it call integers toString or objects toString?
Integers toString.
Any objections?
It depends if integer like overrides it or not.
I mean, integer overrides it. So does it call integers or objects?
Good question.
Okay, so we got some inception going on here. It calls integers. And, you know, you say, but this is a type object. How does it know how to do that? How does it know how to do that? And see, even she's surprised. Like, she has no clue what's even going on. So when you call new in a language like Java or C#, it kind of does a little bit more than you ask it to. So it puts a magic number up here. It puts your actual class data down here. And it puts padding to about 16 bytes. Ask me about this. There's something cool thing that JVM does. Any questions?
Sure. What's the cool thing that the JVM does with
I'm
the
so glad you asked. I didn't think anyone would pick up on that. So, everybody's here at least somewhat familiar with binary, correct? So, if we have something that is 16 byte aligned, what can you tell me about that? Can we make any guarantees about the number?
Yes.
16 byte aligned. What does that mean?
It's going to end in 0.
It's going to end in 4 zeros. So what that means is you can take your pointers and you can shift them right 4 zeros and not have to worry about it. So that means that up to 32 gigs of RAM, the JVM will use 32-bit pointers. As soon as you hit 32 gigs, the JVM will expand to about 42 gigs or 45 gigs because it has to replace all these 32-bit pointers with 64-bit ones. But until then, it's memory efficient. So the header. What is a header? The header is essentially a magic number. It can either be a pointer to a class struct, or it can be an index into an array of class structs. It just gets you to the struct that has all the class info. And when I say all of it, I mean the class name, I mean the class methods, where those lie, I mean the interfaces it implements, the superclass, all of this info. So what does it mean? You can cheaply look up anything about the class just by looking at those first few bytes. If you ever use .class in Java, that's just saying, hey, find where this allocation actually starts. Give me the first 4 or 8 bytes.
Can you go back a slide for like 5 seconds?
You want to see the bear, don't you?
No. How about nesting them? About balking them if I have more than one thing that I'm...
They're all a constant size, or if you're talking about just walking like a list of classes.
Yeah.
Either that, or they're all stored at random places in memory, and it gives you a pointer to them, and you just kind of have to hope that there's a .next or something.
So if I have my special integer that inherits from integer that inherits from object, I have my integer, when I create my special integer, it creates this pointer to this other thing, right? To my integer.
Mm-hmm.
But somehow it also knows. So then in the class for my integer, it has the other stuff to the whatever Java's vtable thing is for integer.
It has a point. The struct, to the best of my knowledge, is a pointer to an array, and the array it's just a list of here's a function pointer to like toString, here's a function pointer to this, here's a function pointer to that.
The object carries function pointers for everything that it inherits from.
There is some massive struct somewhere in memory that has your integer definition. It's like there's a class called super special integer.
Right. Sure.
Here are its methods. Here are all of its stuff.
Yeah.
Here's its superclass, and it knows where to look for that. And the special byte or special 4 bytes, 8 bytes is going to always say, "Hey, go to this struct when you're trying to figure out about this class." Did that answer?
Yeah.
Cool. So what else does this mean? Every time you're not dealing with the concrete class with 0 children, i.e. I'm dealing with list or something, which is an abstract class, you have to do virtual method dispatch. What does virtual method dispatch means? It means instead of call 0x1234, where that's arbitrarily chosen, we have to look a number up into an array, which is where we jump to. So it's a little bit more expensive. That's about it. So the goal of virtual dispatch is, as I presented before, you say object O is equal to new integer. We call integers toString as opposed to objects toString because otherwise you break encapsulation everywhere. In Java, this is implicit everywhere. In C#, you have to mark a method virtual, otherwise you're overriding it explicitly and things become a little bit more hectic. So method calls are more expensive. This guy got his bill. That looks like, so I'm on Dogecoin, and that looked like me when I first got the electric bill, but, you know. So interfaces are even more expensive. And now we get to go into the gory details of all this. So I have class foo extends object, toString returns foo. What would the methods array look like? It looks something like this. So methods array says toString is at this address, wait is at this address, hashcode is at this address, blah, blah, blah. I chose 0 arbitrarily because I honestly don't know what the indexes are and it doesn't matter, no. So whenever we're talking about foo, it'll just say toString is at 0x400 as opposed to 0x100. Is anybody confused by this? Everybody good? Yay. That's exactly how it's done, mostly. Calling class is essential. They're calling toString that. I'm pretty sure that I covered this slide. I practiced this. I'm so proud of myself. So the issue is we can't do this with interfaces. Why? Because if I can implement 30 arbitrary interfaces, how can I guarantee it an index in this all the time? Simple answer is that you cannot. So we have to go through, we have an interface array for each class, and we have to walk through it and say, is this the interface we're looking for? Is this the interface we're looking for? Is this the interface we're looking for? Oh, hey, this is the one that we're looking for. Now we can go into the methods array, and now we can look it up. Now we can call the method. This is expensive. What?
How do you know what interface you're looking for? Because that's...
They have names, they have hash values, they have unique identifiers.
But that's determined at compile time?
It can be determined at compile time or runtime. Runtime, we have all this information as well. I mean, it's determined. You know what interface you're looking for at compile time because you say, here's this type that I have, I'm calling this method on it. And you can look at the class definition and see this method is overriding this one in this interface. So you know there's like a special bytecode for invoke interface as opposed to invoke virtual. So you do know that you're doing it at compile time. You just have to look for it at runtime. So visualization of this is I.compare to for, comparables and interface. So I say integer, go into interfaces, go into comparable, go into methods. Hey, we're at compare to. Does this seem fast to all of you? Just blazing?
Big friction there.
Exactly. Like, this is like Flash. So we did all of this stuff just to call a single method. I'm very happy about this, as you can probably tell by my slides. It's literally my favorite thing ever. And now we're going to get to JITs, or just-in-time compilers. So before we do that, anyone want to take a stretch break? It's been like 20 minutes. Questions, comments? So to repeat his question, because we're back onto this. This question is, why can we not determine where this is at compile time? And my answer is, you know that you're going to be some interface at compile time, but you're not going to know what the concrete implementation of the interface is. And you can have an arbitrary number of implementations of that interface, so you can't just say, jump to this exact space of memory. You have to be like, all right, in this array for this type, where is this interface? Where does it exist? And then you can jump from there. But you can't directly say, oh, this interface, because the table for the interface methods can be arbitrarily long. If we just decided to cram all the implementations of the interface into one.
Maybe a naive question, but why do we need to get through the interface at all when we're defining, when we know what bytecode corresponds to what thing that we want to call at, I assume there's some linking phase in Java. Why don't we resolve the address of the method itself when we're loading our stuff? It seems like we could skip 2 lookups for that.
Because you cannot guarantee a specific place for the method in the class's definition. We're going to get to how this is optimized inside of the JIT.
Okay.
But for right now,
Right.
you have to go through these.
Okay.
Remember, we're not on JITs yet. And so inner JITs, any other questions, any other thoughts? Everybody just seems so interested, so awake. So this is where things get really fun. Also, this is where you can start ignoring me if you want, if you're not interested in these and you're only interested in garbage collectors for some sick reason. Disclaimer, very few people, myself not included, can guarantee when lots of these optimizations will happen. With great power comes great responsibility, etc., etc. Profile before you optimize, because if you make hideous code in the name of optimization, people will hate you. But you can talk about this. It makes you look really smart. I did it once, and I looked smart once, and I was really happy with myself. So what is a JIT? It's a just-in-time compiler. It literally takes your bytecode and acts kind of like a little bit of a GCC or whatever on the fly, and generates machine code, and then instead of jumping to bytecode for your function, it jumps into machine code. It changes... I'll get back to that slide in a second, but it essentially changes this from earlier into that one assembly line. Little assembly line. Does anybody want to ask me about this?
I kind of do, actually.
Okay. So ahead of time compiling is really nice if you're constrained at runtime. Android is finally realizing that ahead of time compiling might be good, which Windows Phone's been doing forever, and you don't really have an option on iOS. But ahead of time compiling is just like your GCC. It's just like whatever you compile with. It's just that it happens when your code gets onto the device, because then you can optimize. You can use every single instruction that the CPU has. Because if I have a brand new quad-core i7, you don't want my processor. You want my processor to be able to run code, but you also want the dude with the 6-year-old processor to be able to run your code as well. So it basically just makes sure that it's as optimized as possible ahead of time. The issue is that when you compile things ahead of time, you don't have runtime information to help you out. So, like, you can't say, oh, 99% of the time this method is called with this concrete class when it only requires this interface. So some runtimes can and do optimize for, hey, 99% of the time this interface, or this concrete class is passed in, so let's see if the class magic number is equal to this, here's this inline method, else do this expensive lookup. Because you can't do that when you're ahead of time compiled. But AOT compiling also means you don't have to keep multiple versions of your code in memory at once. So it's significantly less memory intensive, and it makes your app start up faster because you're not interpreting bytecode and compiling when your app starts. Good? You had a question? Good answer. What's up?
So Java does ahead of time compiling, right?
Java does compiling to bytecode, but this is different. This is compiling to x86 or ARM or whatever machine code.
So you're talking about linking.
I'm talking about once the JVM is running, and once it's actually run your code about 1,000 times, it will transform the bytecode into x86.
Yeah, that's what the part of loading and linking that happens in runtime. Right?
Mm-hmm.
So why are you discrete runtime that compiling? I mean, I'm just confused as to why you are merging compiling time operations with runtime operations.
Because these things are being compiled at runtime. Java does no compile time optimization other than constant holding, or like one or two others that aren't very important. So lots of this optimization happens at runtime. For the CLR, it generally does one optimization pass, or one JIT pass in the beginning for everything, and then calls it a day. Java does multiple. So why do you care? We're going to play a beautiful little game, if I can find my terminal somehow. Yay. So we're going to do jittest.java. Can everybody see it? Yeah. So really, the bottom we don't really care about. It's just this. So our goal is to take n runs, random numbers, and average them. That's essentially the entire goal of this code. It's heavily numeric. For any of you who know about JITs, it's going to be very, very well optimized.
Will it still be well optimized if we don't know anything about JITs?
Actually, no. So what happens is your computer Like, it can sense what you're thinking.
Oh, can smell fear.
Yeah, it can smell fear, and you're just like, am I going to have to go and do flips again? That takes 5 beats of breath. So main is pretty normal. We have this, which I'll explain in a moment. We call it warm-up code. We have this where we actually time it. Is anybody upset with how I benchmark this? Please say no. Thank you. And note that because I wrote this before I chose a name, it's class foo. So I'm not doing like some crazy swap for you. So Java C. Hey, compiled, yay! So it took about 6 microseconds per run, and because I'm great at remembering aha! This option. I didn't practice this at all. What are you talking about? So it took 231 microseconds per run as opposed to 6. That is somewhere around a 30 times speed up.
What is this option? This option?
This option says disable the JIT. Java.compiler equals none means the JIT's entirely disabled. So just enable that and you'll get to see how slow Java is. If you're into that stuff. And that's iTerm. This stuff is just so intuitive, I love it. There we go. So wow, yes, wow. So I searched this on Google and that was the first option. And I'm like, oh, that's actually a place. So does compiling to x86 really help that much? Short answer is no. It's more of a thing where you compile and optimize. Because if you compile, you get speed up. But we can't compile without having all these beautiful optimizations. So why the warm up of 3,000 loops? If this was a CLR, we wouldn't have to do this. Hashtag CLR Shannon's blood. But it's called hotspot, and we had to have something to substantiate that. So essentially, Java won't compile something until it's been run X number of thousand times, which you can configure. But if you're only going to run it once, why have it run really fast? Like, you're going to spend significantly more time compiling this to your code as opposed to more?
Tell us more about how cheating is expensive.
Good one. So, actually, that ties in with this better. But Java can do more optimizations than C and less optimizations than C at the same time. Moreover, it has to use different algorithms because the time to speed, the time trade-off is more pronounced when you're compiling things at runtime. Because if something takes 1.1 times as long to compile and I'm not running it, I'm not going to care because I'm going to compile it once, call it a day. If something takes a little bit longer to compile at runtime, I'm going to care because my code's not running fast. So there are some trade-offs you can make. I know that Go made this trade-off even though it's not JITted, but because they want to have a fast compiler. So their register allocation is a less efficient algorithm, but it's significantly faster than GCC's, if I recall. So they get better compile times, but the code quality is less. That being said, Java is a higher level language. It knows all of this stuff unless you're a daemon and you use JNI. So it's able to take advantage of that. It's able to say, hey, I know you're not going to do anything trippy with modifying this class header, so I can assume it's going to remain the same throughout the entirety of this method without you reassigning the class. And so it's 2 to 4 times slower than C in the normal case. I also want to point that out.
Where does that come from? Did people write enterprise apps?
Lots of Stack Overflow. I honestly can't substantiate that claim. If you want to say, it's 30 times slower because I've got this one benchmark and I included the startup time of the JVM, that's up to you.
I just like the idea of someone writing an enterprise app in both C and Java and testing them.
Yeah. I feel like they do that at some companies, but whatever. So it knows all this, so it can do more optimizations, but like I said, it has to choose worse algorithms when it optimizes so that it can optimize for time as well.
That actually happens quite a bit. People write it in Java and it's too damn slow, so let's write it in C.
And then they do a poor job of it and they have the same problem. But, all right, so I'm going to throw lots of words at you, and then we're going to walk through them in the code. So escape analysis, constant propagation, and then virtual method called a direct method called an inline. I've gone over this last one in my last part, which you should have been paying attention to, right? Right? Everybody pays attention to all PowerPoints.
Of course.
Never. So I'll go over this one first. So virtual method calls, that's when you have to do a little lookup in the table and then you call it, right? If you know what the class is going to be beforehand, why do that? You can make it a direct method call. What can we do to really, really short direct methods? We can say, hey, instead of, doing all this stuff just to get to the method, then execute the stuff, then doing all the stuff to get out of the method, why don't we just throw the method body in here? So that's inlining. So if I have a method that literally adds 2 numbers, what? It costs more to call the method than it does to do the body normally. So why call it? And I'm going to be getting into all this like really soonish, which you all seem so very excited about. So I can type good. I almost shut my computer off. So I manually went through and did all these optimizations for you guys so you can see what the code looks like. And because that's entirely, because you all memorized my code last time, right? You're all good.
Yeah, of course.
So what was line 7 again? I forget. V-split. Oh, that looks beautiful. No. Then why? Okay, I'm gonna see if I can vent in front of you guys. There we go. So we have this method called average rand. In here we got rid of it because we're no longer using it. That's inlining because we took the method. I'm a ballerina apparently. We took the method, we used to have that, and we just kind of inlined it into the for loops. Escape analysis is essentially
Can you put them side by side?
it.
Yeah, I know.
Yeah, it's squished.
You could zoom out slightly and put them side by side.
All right. Do you even zoom, bro? Okay, that's broken a bit, but whatever. Can everybody see?
Yeah.
Okay. So we see there are constants here. Constant propagation is, we know these are never going to change, so why not inline them in the code and have one less instruction, one less thing in a register that we have to deal with. So as you can see, I manually went through, that's 1,000, that's 3,000, all of these are 500. You can see r.next up there. I manually went through the code and saw, like, what is that? And it's just a call to r.next. The cool thing here, though, is that I have this new stack alloc. So what the JVM will do is it will do something called escape analysis. It will see that, I love this so much. It will see that random r is equal to new random is not smart. Would you ever do a heap allocation in C for something that dies at the end of the scope? No? Great, I heard someone say that. So what it does instead is it says, why am I going to do a heap allocation for this? So instead it allocates it on the stack, which is the beautiful operator I came up with, new stack alloc. And it just gives it a pointer to that as opposed to a pointer to the heap. And now magically you garbage collect less because there's less garbage to collect, except for the language itself.
Stack alloc a thing?
It's not. It's something I just kind of came up with on the fly, like what makes sense here?
Okay.
But yeah, I think that's about it. Also, we took this allocation away because all the methods got inlined and we saw that it wasn't happening. So I looked at the produced x86 code a little bit because it will spit out just like pages and pages of assembler for you, and it looks something like this, and I assumed I was right. Like, in all honesty. But I will show you an example soon, I swear. I just have to figure out when I'm getting to it. Thank you, PowerPoint. Here. Correct slide. Magical. So let's go deeper because I sort of lied earlier. Comparable. So who knows about comparable in Java? Who here is programmed in Java? Just about everyone, except for that guy back there who's a BSD fan. So comparable is an interface. From earlier, your reaction should be ew. So let's walk through a few things, namely picks. So who knows what a pick is other than the processor? So what happens is Java generates code on the fly, right? x86 on the fly. So what it will do sometimes is it says, if we have this method that's really, really, really short, we can inline it, just like we did before. So if we see that we're getting, like let's, say that we have integer and t integer, or time lords integer. And they each have two implementations of some interface method. I don't really care what it is. So what Java will do is it'll say, if this code is only being hit by two of these classes, it'll say, if the class is this, execute this inline method, else execute this inline method, else actually look it up. So this is basically, oh hey, polymorphic, so there's multiple, inlined, so it's inlined, cache, so you get money. CLR has monomorphic inline cache, i.e. there's only one, and if you want to see the CLR crash and burn in terms of performance, you give it one implementation of the interface and the other, and you just alternate. And it has to do this really expensive lookup every single time, and it's really great. And I loved it when I had to work on it because it made my code really slow.
Hey, one question. So you said that if Java replaces the code in line, when does that happen? Like what case?
JIT.
Okay, is it okay?
Yeah. Like all of this is happening as Java's, because Java doesn't just do one JIT pass and call it a day. It will do a JIT pass, it'll put timings in there, so it'll be like, how many times was this hit, how long has it taken, and then it'll throw extra code in, see if the extra code is faster. If so, it'll keep it, try different code. If not, it'll throw it away, go back to the old code, try to modify the old code a little bit. So it is constantly trying to make your code work just a little bit faster.
It does that way to see inline.
Mm-hmm.
Just inline. And you talked about the stack allocation, right?
Yep.
Previously, Java doesn't do that, or
Java does do that.
Does do that.
Yes.
Okay, so there has been no object that has been referenced. It will just allocate the object in stack.
Correct. You have no control over that, but Java will look and it'll say, does this escape the scope? Is it easy enough to prove that it escapes the scope? If it doesn't escape, if it cannot prove that it doesn't escape the scope, then it'll allocate on the heap. If it can easily prove that it does not escape the scope, it'll do a stack because then you don't have GC pressure. But we'll see soon that heap allocations are really, really cheap until we get to garbage collection.
Exactly. So allocation in heap versus allocation in stack makes no difference, right?
It does make a difference because you're causing GC pressure.
When you say GC, you mean the garbage collection,
Yeah.
right? But for the execution, it doesn't take place, right?
Correct.
Okay.
You have a question? Okay. So apparently I'm cool and I skipped something. So I want to go to point distance. That's the one. So I have your standard Java code over here where we have a point. It has an x and x and y. We have this distance too, and we have a distance between points method where we pass in x, y, x2, y2. It creates two new points. Find the distance to. Any arguments? No. And now here we have the C version with quotes around it of the code where we just inlined everything manually. Which one's going to run faster? Which one's going to cause less GC pressure? Which
The
one's
second,
going?
of course.
What?
The second.
Sure. Which one's going to run faster? We'll go with that. Because you all know about your beautiful, it can do escape analysis down here. Actually, it kind of helps if I show you the code that's running it, doesn't it? Lol. It literally looks like that. So we just call distance between points. And those are kind of simple to prove that they don't go out of the scope. So GC pressure is obviously the same. Which one is faster? Java.
I feel like the second one should be faster. I don't know why it wouldn't be.
Same speed.
Oh.
Exactly. Like within 1 microsecond. So, if you really want to make your code C-like and you want to make people hate you in the name of optimization, please make it Java-like first. Please don't make it Java-like first. Please make it sane first. I'll put it that way.
Okay, what's that?
Yep.
Can you do the compilation without the JIT and
Sure. What? They just work, guys. Don't know what you're talking about. 8 milliseconds versus 58. So without the JIT, there is a significant difference. With the JIT, it's the same. because I tested this like 8 times to make sure it would work properly.
Which I forget which one's which. The C-like one is the one that took 10 times longer?
C-like 1 is raw.
Okay, yeah.
Java like 1 is point.
Cool.
Because obviously you're allocating a lot, you're doing all of that stuff, whereas with the JIT code, it's going to be roughly the same unless my computer hates me.
Is that
Which it
example
does.
from CS3114?
Hmm?
Is that example from your CS3114?
No, I made it up.
Okay.
We don't go over efficiency in that course.
That's true. We
Well-
use points, though.
Yes,
Never mind.
we do use points. Also, because I really don't feel like going back to my slides right now, the keyword final, who can tell me where it can be used?
It's like constant, so you don't have to change it.
Mm-hmm. Where else? Anyone know?
Classes.
Yep.
Method,
Yep.
class is a
So which of these makes your code faster? Constants, right? Because I showed earlier that they can do constant propagation. Does that up there make it faster? Public final int x, public final int y? A little bit. A little bit. It can put it in a register and guarantee that it's not going to change when you call a method. It's a little bit trippy, but a little bit. What if I put it on a class or a method? It would help to know that the JVM is smart. Smart.
Wait, why does registry allocation change when you assign final?
If I have a method I'm calling on something, the something is a pointer back to me, it can change my x inside of the sub method, and then I can pop back, and x is now changed. Did that make sense, or was that way too abstract?
So it's not pushing from to do a memory access. It's not a method, right?
Yeah. So if I have class foo with x, right? And I have class bar, and it has a reference to a foo. Cool.
Yeah. In Java, I can just have a pointer to X.
You can have a pointer. If foo is calling a method from bar, that method from bar alters x.
Oh, sure.
You come back up. Without final, you can't guarantee that it remains the same. So it can't. Yeah. So methods. I put final on a method. That means it can no longer be overridden. Guarantee never overridden. Does that make your code faster? Because Java doesn't have to do virtual dispatch anymore? Theoretically. Same thing for the class. I put final on it. It means it can never be overridden. Java doesn't have to do virtual dispatch on anything anymore. So theoretically, yes. But in actuality, no. What it will do is it'll say, hey, is there anything that is actually overriding this class at this very moment? No. I can do all these pretty optimizations. And I'll just add a note to, hey, if something is loaded that overrides, or something is loaded later on, I can just kind of throw this version away and recompile it less or more conservatively. And that's kind of why AOT loses to JIT in pure speed tests, because it can make all these assumptions and it can just note, I made this assumption, if this changes, I can just recompile it. AOT's like, I can't make this assumption, what if it changes? So I said that. JIT's done. Everybody's happy.
No.
I don't care.
Wait.
So stop, breathe, stretch, questions. I will give anybody else priority over him. This is a priority queue based on age, and you are the smallest. Everybody, other than Time Lord, good? What's up? You forgot.
So what about caching the optimizations in between runs?
That can be done. It's not like standard for the JVM, so I can't comment on it.
So then, why? It seems like such a logical thing to do, because
I agree, but I'm not going to try to make like an argument for or against it because I don't know the machinery that's going on, like absolute behind the scenes.
Okay.
So
And
maybe there's something that it can't like hold a pointer to or something. Maybe it's just stupidly hard. Like I know that lots of games, when you click save, it's just a dump from a structured memory, and they're hoping that it's never going to change.
Even for like inlining stuff though, like should I inline this or not? Oh, it got inlined. Let me make a note of that. Like, no?
Your code could change
Fine.
between runs.
And then, damn, I did forget. Oh well.
You'll remember. So,
So your main point is that by adding qualifiers, you make your code faster, or is your main point that JIT does not care if you add qualifiers or not?
For some parts of code, like when you're saying this code will not be overwritten, the JIT will not care. It will. I think it literally throws the keyword away and doesn't even listen. Like doesn't even acknowledge its existence. It's just there as like documentation. But lots of people will say, adding final, it means this, therefore it will make stuff faster. When in reality, the JVM is smarter than that. It knows to optimize for the normal case, which is where you don't have final, but there's also nothing subclassing it.
So you're saying that the qualifier that we learned in classes makes no sense in JVM?
Final for methods and for classes is not going to speed up your code on modern JVMs. On older ones or on poorly made ones, it might, but on the hotspot one.
And is there any qualifiers that you have come across that make code faster?
Final on local variables?
No, in the new JVM. Any qualifier that you have come across outside this code?
No, as far as I'm aware. So,
Yeah, what context is the compiling actually done? Is there like another thread that runs separately, and then when it's time to link in the optimized code, it like locks everything and then
that's
does
a very
it? Or
interesting question.
Also, what about on single?
That's a
processor
very
machines?
interesting question because the JVM can JIT a loop body, but not the rest of the method. Because it sees you're in a loop body 30,000 times and you're in the method once. So it'll say part of the way through the loop, I'm going to compile this and then do a hot code swap. I'm not quite sure. I know that JVC Java bytecode is not meant to be like fast in its design. So it might just have checks. Is this compiled now? Is this compiled now? Is this compiled now? You'd say that would make things really slow, but if it needs to be fast, it's going to be JITted. So I can't. TLDR, moving away from the politics answer, I can't answer your question because I don't know. But I'm pretty sure it's a separate thread because I've run many one-threaded or single-threaded things with the serial GC and I've seen CPU usage go over 100% for Java. So final stretch. Garbage collectors. There are multiple kinds, there are multiple traits you can tag onto them. There's generational and non-generational. Guess what's mutually exclusive? There's accurate and inaccurate. There's parallel and serial. There's rep counting, which some people don't even consider garbage collectors. And there's mark and sweep, which most people consider garbage collectors. We're going to go over generational, accurate, and serial in this one, and the rest of it just kind of leave out. Also mark and sweep. These are all traits on the same garbage collector. And I want to make a note about inaccurate versus accurate. Accurate says it'll grab everything. Inaccurate says it might have some inaccuracies. Like there is a garbage collector called the Boehm collector. It is a C garbage collector, as in it garbage collects C. What it does is it runs through all of the code, all the areas you can have data that's mutable in your program. And it's like, does this look even slightly like a pointer into the heap? Yes? Cool! That you must have a reference to that. Let's not throw that bit of the heap away. So that's what we mean by inaccurate. If you have a float that just looks perfect, you can have something that never leaves the heap. In civil languages like Java, JK, no one considers Java civil, we can do accurate because we have all the class information about all of its fields, all of this magic that the garbage collector can use. Everybody, by the way, knows this, at least at a very, very high level, what a garbage collector is. You call new, it picks up after you. Cool. So the JVM has more than 4 standardized GCs. I'm going to go over one of them. You can swap between them all that you want. You should profile. Some people get faster on one, some people get faster on the other. Some of them are still magic to me. So here's the GC's picture. This is serial because it kind of looks like a dirt. And the rest of them are Taka trucks. So they're kind of GCs. So the standard GC has been G1, which is literally what they call it since JDK 7, so like 2 or 3 years from now. It's a little bit more complex than concurrent mark and sweep, so I'm going to go over CMS instead, except for without the concurrent part, because that makes life a little bit more difficult, and by a little I mean a lot. The basis is similar. CMS is concurrent. It's mark and sweep in generational, which I'll go over soon. Like I said, we're ignoring concurrency because YOLO. VTLUUG, if any of you were into Ruby, MRI uses generational market sweep as a version 2-ish, maybe? Market sweep for allocation, and all allocations that has been made, if it has references to it, mark it. For everything that's been marked, keep it, else throw it away. Was this profound? Did this confuse anybody? Is everybody on the same page? So generational. The foundational things that you have to know to understand arithmetic, garbage collectors in Java, is that pointers, you can't access the pointers, right? Like if I say give me the raw pointer, what memory address is located at, you can't get to it without some crazy J and I stuff, correct? So that means that Java is more than welcome to change them out from under you at any point. It's beautiful. So what happens is standard garbage collection, if this was not generational, this was just normal, is say I wanted to allocate something. I have a pointer to here. It goes here, pointer is now here. Allocate something else. It goes here, pointer is now here. Lose the reference to that. Oh well, new thing. It goes here, pointer goes here. Okay? So I allocate something else. Let's say I decided to read, a Java program. So 4 gigabytes. And then an image, another image, and now we're out of memory. So what happens is it runs through, says this use, this use, this use, this use, this use. It's not actually doing that. It's tracing from like one of these and the stack and all that to what's actually used. But we're just going to pretend, for the sake of, we're going to actually learn the real thing in 5 minutes. This use, this use, this use, on. And whatever's used, it'll move out to this magical space. So we're going to pretend that's not used because I want to draw it. These 2 things are used, nothing else is. So this extra magical space, these 2 things have been moved, all the references have been updated. This whole thing is now free. We can put the pointer here again, zero it out in front of the allocations. We're good.
What is known?
Long story short, because I will go into I will go slower.
Okay, but that's the part that's done the fragmentation and defragmentation, right?
This is what's now been scanned, and it's all free. This is what I was holding on references to.
Okay.
So essentially the goal of this is to show I don't have to go back and free up stuff. I can just go through this, and then when I'm out, I can check to see what's actually used. I can move it around, and your program won't change.
Can you go back to market suite? No, it's serious.
Okay.
How do you know when it's no longer used, besides rough counting?
So this was, like I said, kind of an inaccurate view. What it does is it has a few base points that it goes from, like globals, stack, and when you did registers and things like that. And it essentially says, what do these point to? Okay, what do the things that they point to? Blah, 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 until you've traversed the entire reachable object graph. And then it finds where all those are, it moves them all out to here, it marks this entire thing as free.
So when that thing is full, it takes an atomic snapshot of all objects, traverses all of them.
It depends on your garbage collector.
Okay.
It really depends on your garbage
But in
collector.
general, is that
It doesn't take a
done?
snapshot necessarily. It can entirely halt your program to do this, which is where you get these magical, it's like 2 milliseconds, 2 milliseconds, 3 seconds, 2 milliseconds, 2 milliseconds, 3 seconds.
Yeah.
There are also ways to do it in parallel, which I will get back to at the end. Just ask me, because I really don't want to put these people through memory mapping. I feel some remorse for them.
Would you if we asked nicely?
What?
Would you if we asked nicely?
Yes, you guys, like I said, pretty please. So, generational. This was a lie, like I said, but it was good enough to demonstrate a point. Don't you love how I lie to you, and yet I tell you the truth anyway? I'm like man's best friend or something. Anyway, so we've got 4 generations, essentially. We've got the Perm Gen, Eden, Survivor, and Tenured, which I'm going to get into. Perm Gen is like your class files. It used to not be collected, now it's collected because people are like, oh, people are actually making languages that aren't Java for this, and they're doing crazy stuff. We need to make up for that. Hashtag closure, even though I love it. So, it's rarely garbage collected. It's These are things that are expected to live forever, so if you load a class file, you will unload it at some point maybe, but generally doesn't change. New gen, new allocations, it was the thing with the pointer that I was showing earlier. Old gen, I don't know how I got that picture, but I got it somehow. I think I searched like holy crap or something, and then it's kind of creepy. So it's old allocations, and survivors are teenager allocations. So how this works is we've got Eden, which is our thing with the little pointer. That's new. This is courtesy of Oracle, by the way, so I guarantee that it's as right as the Oracle engineers can make it. So once you hit the end of it, and I'm sorry that I'm favoring this one, but camera, for all those new people who walked in. So anything that lives past this first garbage collection, i.e. you still hold a reference to, is put into one of the two survivor spaces. And then goes through again, garbage collects. By the way, most of the time, the tenured/old is no longer, like, it isn't being garbage collected when I'm talking about this. There's two different types. There's Eden GCs and full GCs. I'm pretty sure you can infer by the name. If not, please come see me because you need help. So we garbage collect again. Things go into the other survivor space. Garbage collect again, as well as one of the survivor spaces. Anything that's still in this survivor space then gets tenured because it's lived through 3 garbage collection cycles. And we need space there. Garbage collect again, anything that's in this one then gets tenured because it's lived through 3 garbage collection cycles. We need to use the space again. Are you seeing the pattern? And then eventually we go into tenured and we garbage collect that as well. Ignore the virtuals if you don't know what virtual memory is. If you do, it is like if you say I want a 256 meg heap or a maximum of like a 1 gig heap, allocates the 1 gig and then it actually allocates memory as you go on. Everyone?
Does this map to how it's actually laid out in the address space?
It is courtesy of Oracle, and they said this is literally how it's laid out, and I wouldn't disagree.
And then how about where things are placed
How do you mean?
within the address space? Obviously, we're not going to go to the 64 anytime soon, but you said there was that Magic 32 pointer business, which makes it actually somewhat important how big I make the sizes in the beginning.
It could be a pointer, or it could be an index into a global array. So if you have 2.1 billion classes, you're going to have an issue. But until we hit that, well, 4.2 billion because unsigned, but until you have 4.2 billion classes, which I'm pretty sure Google is reaching soon, or Microsoft. Does everybody understand this? We move things over to each one of these, and then we eventually move them to tenure that they live. So this is going to seem expensive because we allocate something. Every single time we move it, we have to run through our whole program and be like, all right, what's pointing to this? Let's update where it is. Well, I'll get to that in a moment, apparently. I'll get to that in 10 minutes. So what does this mean, though? It means that allocating is really, 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 really fast. New is essentially result is equal to grab me the pointer in Eden, add it to size of new object plus 4, and align that to 16 bytes, return result. My bad. Align that to 16 bytes, return result. It's 16 byte allocated alignment, it's just a pointer bump. When parallel happens, life gets a little bit more interesting. It's not stupid as you would think of it, as in there's an atomic number that's kept. It actually will segment it into different parts for different threads and do crazy stuff. So yeah, it's cheap. Already said that. Isn't this like high overhead? Empirical says no. This is a graph of essentially how many bytes are allocated and how long it lives through how many collections. I think it's 90-95% of allocations don't live through more than 1 garbage collection. So if most of your objects aren't getting moved, aren't getting collected, you don't want to walk through most of your objects. So that's why they took this path as opposed to some other thing where it was literally walking the whole heap.
Can you explain that again?
Hey,
All right.
so when you say garbage collection, is there a separate garbage collection for instructions and separate garbage collection for data?
They all use the same garbage collector. It's just when the garbage collector runs on them. Because you will have a garbage collection pass on Eden or a garbage collection pass on everything, essentially. So it's just when it does the different ones. Like here, as you can see, minor collections, those are collections of Eden, so that's minor, 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 minor. Major are significantly more spaced out.
Because to me, it looks like this is not the most optimized version because we're actually spending more time moving stuff in the name of garbage collection, right? That is, you can just do the entire memory and start allocating stuff.
I mean, like I said, 90-something% of the time, you're not going to move the objects that you called new on. So if you don't traverse 90% of the objects that are allocated, it's not going to be, like, you're going to be saving a lot of time not doing that. And considering that most allocations are, oh, hey, allocate this 16 or 30-byte thing, 32-byte thing, rather, and then you have 5 gigs of heap space to run through, that's a lot of 32-byte, 16-byte things.
So initially I was confused about when I update something, I have some other object that's already tenured.
Mm-hmm.
Suddenly it has a pointer to some other stuff. I make a new thing, and I have a point to it, and so all of a sudden I have the scale reference and something that's already tenured pointing to my other, pointing to something in Eden, and if I'm only garbage collecting things in Eden, it'll look like it isn't used because my only pointer to it is from a long-living thing. However, is that why everything is immutable? And so when I would update my tenured thing, then all of a sudden that would go away and I'd have a new one in Eden? Is that
That
how it's
goes a
resolved?
little bit with the parallel thing, so I'll get to that at the end. But you have picked a good point, and they had to do quite a bit to make sure. It will go through some of the things on Eden. It will see what has been updated on Eden, or not on Eden, not on old gen. But it is allowed to be imprecise such that it will walk things once, and then it will, if you keep old references to things that are no longer referenced, it doesn't care because it'll catch it all in the next garbage collection.
Oh, sweet.
Yeah.
So, yeah, okay. So an Eden pass could have false negatives.
False positives for what is still alive.
Sure. Okay.
Yeah. So
Do you know like how often that happens in practice?
I have no clue how often that
Okay.
happens, but not very often unless you're using one of the parallel collectors, and even then very often it's like 10% or less. There are exceptions, not like the throw kind, but like if you make an alloc that's greater than like 2048 bytes or something, it'll be put into the perm tune automatically because they saw by empirical evidence that these 2048 bytes will live longer. There are exceptions. So takeaways, GC, garbage collection passes are expensive. If you have enough RAM, you never have to run them. So just download more RAM, put that on a loop, and you're good. We made it. We made it. We're alive. It's great. I can ramble about other things. Are there any questions on garbage collection at all? Okay. So I can ramble
Could you
about...
expand on that download RAM portion?
So there's a site called downloadmoreram.com, and it's a great website. I highly recommend it to...
Can you pull it up?
Yeah. Can you download some RAM?
So I'm going to download RAM right now. Actually, I think I need to ping him on IRC so I can download him.
Mm-hmm.
I know you can't see it. I'm just making sure that I don't mistype it and get to some like weird site.
Do you have another section, or could you go to the parallel stuff?
So you can download, click download now. It has a little...
Oh, they have
cement
4
thing so you know
gigs
it's
now.
legit. Yeah, they do.
Oh.
We're never sarcastic in here. So I can ramble about stuff if anybody has specific questions.
Parallel, everything.
I hate you. So essentially what Parallel does and how that ties into the old gen a little bit is there are some implementations that will map the old gen as read-only. As in, it'll take away the ability to write. And it will start scanning the object graph in parallel and just mark whatever, like your registers and your stack and stuff, is dirty. And when something's written, it'll just say, all right, we're going to mark this page as dirty. We're going to give them write permissions, and then we're just going to rescan that in serial. So lots of your scanning can be done in parallel, and you know where to come back to, and you know what's been touched. So you can just go back to that really fast. So 80%. I don't know, I'm kind of just pulling it out of thin air. But is checked in parallel, and then the extra 20% is checked in serial, and it's called parallel. There is no existing garbage collector that never stops the world. And by stopping the world, I mean stops code execution at some point for some reason. There's one garbage collector called the pause less garbage collector, which pauses less than normal, but it requires its own operating system, which is like a fork of Linux to run because they need really fast system calls because they map pages in and out really, really often, and they do all this crazy stuff with it. I have no clue how it works, but apparently it works really well for like enterprise environments, and it costs a lot of money. Anybody interested in any of this at all? All of it, none of it? Tired? Want to go home?
Can you go over bounce checking a bit?
Sure. So, I have this code. Let's say that I have an array of I. I want to print it for I equals 0, I is less than array length. I don't care. I plus plus. So, this is entirely compliant Java. I don't know what you're talking about. So when this gets compiled, you're going to have an array bounds check every single time you get there, right? Because you want to make sure it's not out of bounds. The JVM can prove I is going to be within these constraints, so it can lift the bounds check up to here, so you only do it once, maybe not at all, and it lifts it out of the loop essentially. And this goes with regular code optimizations where if you have a constant that you're checking an if statement every single time, things like GCC will lift that out of the loop as well. And sometimes it'll just generate 2 loops for you because if you're checking a constant every single time, there's no point in checking it every single loop. I've gone through JVM and CLR. The beauty of a JIT is that it can do architecture-specific stuff. When I was doing this talk, I was looking through the assembly that the JVM generated, which when I said it's pages, it's literally pages. Like before it even hit my code, it's like, oh yeah, we did these 12 methods from ToString, and they're all like 300 lines of assembly long. And I wanted to cry myself to sleep because it was 2 a.m. But too bad I had an energy drink 5 minutes beforehand, so I couldn't. So I just cried. So it had lots of things like all the beautiful vector instructions. I think that even one point it had like some weird thing where it called one of the AES instructions. But it's all specific to the processor and this forward-thinking, expensive piece of crap. It can do that because it's compiling. It knows exactly what architecture it's running on. It knows exactly what the cache size is, and there are actually things where it says, oh, this instruction would be 1 clock cycle faster, but it's more likely to cause a cache miss, and because this is in bytes of cache, it's crazy. But JITs can optimize your code so it runs a little bit faster than ahead of time, is the entire.
So, for Android, the environment is pretty much homogeneous, where we have some ARM thing that has some relatively the same amount of cache, relatively the same blah, 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 blah.
I don't make any guarantees because that's Dalvik, and that's a heavily tweaked JIT that is tweaked to be memory efficient as opposed to CPU efficient, as of the last time I saw it. And because I don't have an Android, I don't keep up with it very often.
So why are they jitting? Because
they're moving to ahead of time as of 5.0 because someone said, hey, this might be a good idea. We can catch up with Microsoft. No one ever thought they'd say that in their lives.
fine.
Yeah.
I mean, for enterprisey things, even forget Android. For enterprisey things, we can say, oh, this is going to be running on like some Xeon. They pretty much all look the same.
Heterogeneous computers.
Fine. The person, the sysadmin installing the damn thing can say, this is what it's running on. I have like an example workload that I can throw at it. Let me do that now. Have it JIT everything, and then save that. And you can kind of treat that as a compilation step. And then you just generate your bytecode, or your native bytecode. You load your native bytecode at load time, and then you just execute that. And you don't even have magic shit besides the garbage collector. The JITting is entirely pointless because it's all native instructions anyway, and that would save you, I would imagine, tons of time.
Really
what?
Do that first step though. I mean, you don't know until you're actually in the final environment how many times like this loop is going to run, like how much.
Right. That's why you have a dummy workload to throw at it. Or you take like 10% of your live traffic and you throw it at your box that's currently JITting things.
That being said, you you have to see how much time that's going to save you ultimately, because
But it's going to save you some time, and that makes it worth it.
of admin time.
Yeah.
Like
Yeah.
a lot.
it's going to
It
save
could
you
be
some
entirely
time,
automated.
but so will some optimism. So will including like the more expensive
And it
register
might make
allocator or whatever.
I mean, like, essentially, if you're doing the profiling as you're building, like, as a build step, like, you could potentially make it worse. You could, like, because your profiling could just be wrong. You know? I mean, if, for example, it's a web server, and you try and run it a couple of times with, like, totally not, like, the correct load, then it's not going to help at all. It's going to make it worse.
There's no web service.
But
Doesn't
there are many
launch and then
cases
got
where it's-
unexpected volumes of traffic.
Well, yeah.
But there's many cases where that's not true.
I guess that's true,
You-
but I mean, it requires a lot of like knowledge about exactly how your project is going to be used, which I think is almost never like available to you as you're building it.
So I'll comment on both sides of this. On the side of pre-profile or profiling or whatever, lots of people do this when they're trying to select garbage collector and things like that, because there are certain garbage collectors that will perform significantly better than others. Like if your workload is incredibly parallel, you might not benefit from the GC running on all the cores. You might benefit from running it on one, whereas if your thing is single core, you would benefit from it running on a different core if you have more than one core in your machine. That being said, JIT should not be significant enough part of your runtime. It's going to be significantly less than garbage collection at the very least. Unless you're just writing scripts in Java, in which case I would question your practices. But it shouldn't be a big enough impact where all of this extra work is necessitated. Unless you're on one of these babies that has like an eighth of the power of this.
Which is still
Yeah, it's still a decent amount of power, but it still hurts startup a bit.
it's like my final server.
Yeah.
So I have a question.
So,
Why, and sort of ties into his question, why wouldn't you JIT the thing and then cache the JIT state of the thing?
that's ahead of time compilation. If you want to add the JIT into it, then you help startup time a bit, but you're not. That's the only thing that you're really gaining is startup time. Is it not?
No, it's not. You're gaining runtime too, because you don't have to do all these checks as it's executing, and you don't have to be like, oh, hey, we're going to make some use some genetic algorithm to JIT certain things and inline certain things and then see if it's faster. You can totally ignore all of that.
You're saving some startup time because you can say on the first time you call this, please JIT it. Now, you are saying, here's this thing that it took us 12,000 runs of this to get to and agree on that this is just about as optimized as it's going to get. But once again, I'm not saying it's a bad idea. I'm saying it's adding a fair amount of complexity potentially, and that the performance gains might not be warranted. Especially in server environments where you're like, if this takes 5 minutes to start up, so long as it's as fast as I can get it, I don't care.
Yeah. Well, I guess what I was saying is not so much like ahead of time compilation as like you're gonna just in time, you're gonna JIT the thing, right?
Mhm.
At runtime, and before the JIT decides that we need to JIT this particular loop body or whatever, you're gonna run the loop body over 30,000 times.
Mm-hmm.
So, I ran this, and I ran this loop body 3,000 times.
Yep.
So, next time you run this, here's the JITted version, just do that.
It just saves its own state.
So yeah,
Mhm.
so save the state of, cache the state of the JIT
Yep.
with the execution run.
I mean, like I said to him, I don't disagree that it's a good idea. It's just the complexity time trade-offs.
Yeah, so I guess I was just asking if there was a complexity time trade-off.
There is. It is apparently significant complexity and, I don't know, not enough time to warrant trade-off.
Thank you, dyreshark.
What?
Thank you, dyreshark.
You're welcome. I'm glad I could help.
Okay, so what are the advantages and disadvantages of the JVM versus CLR? Briefly.
Briefly, okay. So the JVM was made much more for server environments.
Not briefly.
JVM server, CLR, phone, desktop. Like I said, the JVM will continually see, is there any way I can eke out a little bit more performance, even though it was originally made for set-top boxes. But I'm saying, at the moment, I caught myself there. At the moment, it seems more like it lends itself to servers than to desktops, whereas the CLR is, let's do one pass over this, let's do kind of a good job, and I can't say the best that we can because I've seen the code and it isn't the best that they can. So let's do kind of a good job, and let's just leave the CPU to other apps because this is most likely going to be a phone or a desktop. So that's kind of the difference in how I see the ideology of the two. One thing that everybody always brings up is reified generics, and I'm going to explain those for 2 seconds.
Yeah,
I wasn't going to bring that up.
Someone always brings it up. Essentially, who knows integer versus int?
Unboxing.
Everybody ever. So, integer is a pointer to a heap allocated immutable int. Because every generic thing in Java is essentially object. The generics are not saved at runtime, which allows for some cool hacky things and some ugly, expensive things. CLR says, all right, we can generate a list parameterized on int. We can generate a list parameterized on double. For every value type, i.e. int, double, whatever, with a lowercase, it will generate a special code path for it. For every reference type, i.e. object, integer, whatever, it'll just pass it all through the same thing. Because it's like, we're dealing with pointers anyway, and we're just going to we're going to have these casts to make sure that it's still logical. So that's one of the differences. The JVM's like, hey, let's not break backwards compatibility. Let's just make you box everything into integers so that your array list of integers takes exactly the same amount of space as an array list of longs, but, it's kind of more worthless. CLO is like, hey, let's break all the backwards compatibility, #Windows 8, and make things better. These are apparently coming in Java, not ints, but reified generics, as of Java 13 or so, which is a long ways away.
Does this interact negatively or with things like the CPU does to, like branch prediction? And
so branch prediction, as I am aware of it, is more of, was this true in the past, and based on was this true and can we find a pattern, let's try to guess this. It definitely does affect performance because you have to have a pointer to something, you have to go to the pointer just to grab the integer, you have to pull the integer in. You also have to do null checks implicitly, but it's going to slow things down, but I'm not so sure that it would mess with branch prediction as much, except for just adding more null checks, which means that stuff might get pushed out of the branch predictor, because as far as I'm aware, we haven't found a way to fit infinite things into one small space. So things would have to push out of the branch predictor eventually.
Total speculation, but I'd imagine what would mess the branch predictor more is the jitting of the code itself. But
yeah.
Since it's going into a different address anyway, it depends on your predictor, but usually the statistical stuff that generates your hints would be different because it's at a different address anyway.
Yep.
And so it's fine. As long as you don't keep reusing the same address and screwing yourself, it's not.
Your code L1 loves you when you run the JVM. It gets so much use. Any questions at all? Even V8, I might not be able to answer it, but V8, CPython.
Yeah, so there's this magic LLVM JIT stuff.
Magic LLVM JIT stuff. What about it?
Overview?
What?
Want to give an overview?
So it has an intermediate language, as all JITs do. The intermediate language is standardized. The intermediate language is lower level than that of Java bytecode, is lower level than that of CIL. And you can either ahead of time compile it, i.e. client. You can call in the libraries to just-in-time compile it, i.e. Julia, which is a really cool language that all you should check out if you like, pre-beta software. I can't really speak a lot to it. I know that there's a tutorial on how to build your own language in Haskell that calls into LLVM to JIT it, which was really cool, and I'd never looked past chapter 1 because I'm lazy. Also, it was like, you need to know monad transformers, and da-da-da-da-da. And I'm like, I know the first word of that, but I'm going to learn eventually. I can't really speak, I'm sorry, to LLVM much because I will be able to soonish, but not at the moment. Anything else at all? All right, summary time. Not getting summarized on one slide. They're cool. They do a lot for you. They can take a lot of memory. I like to say it costs an arm and a leg. Did you catch that? So the JVM can be summarized by let's throw every optimization we can possibly think of and see how it performs. It apparently does well. Sometimes brute force is the answer. Has lots of garbage collection algorithms. Profile, then optimize. I don't want your boss calling me and be like, I heard you gave this presentation and they've been doing all of this stuff ever since, and I literally hate you. And then I'd just be like, hi, I don't know you. Remember distance 2 thing? It will optimize for you without, you have to have the abstract factory adapter facade visitor pattern goodness. There's actually a website that will generate class names like that, and I've kind of used it for one of my projects, and I kind of thought it was hilarious. So thank you for your time. We lived through it. It's an hour and 20 minutes. I'm glad you're all awake.